When a scientist makes the same measurement twice, the result is often different the second time. This does not mean that the scientist made a mistake. The reliability of a measurement is often limited by the tool used. For example, it is hard to measure the length of a highway with a meter stick. When reporting a measurement, a scientist must give an indication of the measurement's uncertainty. First main idea: accuracy is different from precision. The terms accuracy and precision mean the same thing to many people. However, in science, they have very specific meanings. Accuracy refers to how close the measurement is to the correct or accepted value. Precision refers to how close a set of measurements, made in the same way, are to each other. Measured values that are accurate are close to the accepted value. Measured values that are precise are close to one another. Imagine that 4 darts are thrown at the center or bullseye of a dartboard. The accuracy of the throws is determined by how close the darts land to the bullseye. The precision of the throws is determined by how close the 4 darts land to each other. For an example of high precision, examine the 2 dartboards on the left, A and B. In both cases, the darts landed close to each other, so the dart thrower was precise. However, because the thrower was attempting to hit the bullseye, the thrower only threw accurately at the dartboard on the far left, dartboard A. If you want to see an example of high accuracy, we can look at the dartboard only on dartboard A. This dartboard shows that the thrower was accurate. In scientific experiments, it is important to be both accurate and precise.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests that the experiment has accounted for all factors that might affect the system being studied.
Percentage error. The accuracy of an experimental value can be compared with the correct or accepted value by calculating its percentage error. To calculate the percentage error, subtract the accepted value from the experimental value, dividing the difference by the accepted value, and then multiply by 100, according to the equation on the screen here. Error in measurement. Some error or uncertainty always exists in any measurement. For example, the skill of the measurer places limits on reliability. The measuring instruments limit how precisely a value can be determined. In addition, the readings from balances, rulers, and graduated cylinders are controlled by how fine the markings are on the instruments. To demonstrate this, consider the ruler on your screen here. This ruler can be used to determine the length of an object precisely to the tenths digit. You can tell that the nail is definitely between 6.3 centimeters and 6.4 centimeters long. However, it is hard to tell whether the value should be read as 6.35 centimeters or 6.36 centimeters. The hundredths place is somewhat uncertain, but a reasonable estimate of the digit can be made. You might include a plus or minus value to express the range, such as 6.36 centimeters plus or minus 0.01 centimeters. Fifth main idea. Significant figures are those measured precisely plus one estimated digit. In science, measured values are reported in terms of significant figures. Significant figures are all of the digits known with certainty plus one final digit that is estimated. To demonstrate this, let's consider the ruler again. The length of the nail in the photograph is given as 6.36 centimeters. All three of these digits are significant, even the uncertain digit. All contain information and all are included in the value. The term significant here does not mean certain. In any correctly reported measurement, the final digit is significant but not certain. Insignificant digits are never reported. Determining the number of significant figures. If a measurement does not have any digits that are zero, then all of the digits are significant. For example, the nail's length on the previous screen of 6.36 centimeters has 3 non-zero digits, and therefore 3 significant figures. However, the digit 0 can be significant or not, depending on how it is used. The rules in the table that are on the screen here summarize how to determine if a 0 is a significant digit.
Rules for finding significant zeros help you ensure that the numbers you report are accurate. Zeros appearing between non-zero digits are significant. We count these zeros when determining significant zeros. Zeros appearing in front of non-zero digits, however, are not significant. We ignore these zeros when determining the number of significant figures. Zeros appearing to the end of the number and to the right of the decimal point are significant. These zeros are only written as part of the number when they are significant. Zeros to the left of the decimal place, however, have to be written whether or not they are significant in order to designate their place. If you measure exactly 200 milligrams of a substance, then the zeros in this number are significant. If, however, the zeros are just placeholders to indicate 200 milligrams as opposed to 100 or 300 milligrams, then the zeros are not significant. Rules for finding significant zeros help you ensure that the numbers you report are accurate.
Rounding. When you add, subtract, multiply, or divide two measurements, the reliability of the result should be reflected by its significant figures. How the result should be rounded is determined partly by the rules given on the screen here. A measurement's rounding is also determined by the operation: addition, subtraction, multiplication, or division.
Rounding rules help you ensure that the significant figures you report in a measurement or calculation are accurate. Once we find the digit following the last digit to be kept based on the rules for significant figures, we ask the following questions. Is this number greater than 5? If so, we round up. Is this number less than 5? If so, we round down. Is this number equal to 5? If so, we have more questions to ask. Is the next digit after the 5 greater than 0? If so, round up. If the next digit after the 5 is 0, then look at the digit before the 5 and determine if it is even or odd. If it is odd, round up. If it is even, round down.
Addition or subtraction with significant figures. Consider two mass measurements, 25.1 grams and 2.03 grams. The first measurement has one digit to the right of the decimal point in the tenths place. There is no information on possible values for the hundredths digit. If you add 25.1 grams and 2.03 grams without considering significant figures, the result is 27.13 grams. However, it doesn't make sense that the sum is more precise than one of the individual measurements. Therefore, when two measurements are added or subtracted, the final digit of the result should be significant in both of the original measurements. Multiplication and division with significant figures. A calculator often gives many more digits than are justified by the measurements. For example, suppose you use a calculator to divide 3.05 grams by 8.47 milliliters, a density calculation. The calculator would show a numerical answer of 0.3600944451. The answer contains digits that are not justified by the measurements used to calculate it. For multiplication and division, the answer can be no more significant, meaning contain no more significant figures than the measurement with the fewest significant figures. Conversion factors and significant figures. Earlier in this unit, you learned how conversion factors are used to change one unit to another. These conversion factors usually do not have any uncertainty. For example, there are exactly 100 centimeters in a meter. If you were to use the conversion factor 100 centimeters per 1 meter to change meters into centimeters, the 100 would not limit the degree of certainty in the answer. A counting measurement is also exact. For example, suppose you have 10 test tubes, each containing 5.67 milliliters of a liquid. The number 10 is exact. It should not be a limit to the significant figures in the calculation. You can safely report that you have 10 times 5.67 milliliters, or a total of 56.7 milliliters of liquid. Sixth main idea. Scientific notation is used to express very large or very small numbers. Sometimes measurements are very small or very large. It is often awkward to give measurements with lots of zeros, such as 23 quadrillion, or 0.0000000000000000179. Instead, measurements are often given in scientific notation. In scientific notation, numbers are written in the form m times 10 to the nth power, where m is greater than or equal to 1, but less than 10, and n is a whole number. When numbers are written in scientific notation, only the significant figures are shown. For example, To write 65,000 kilometers in scientific notation and show that the first two digits are significant, you would write 6.5 times 10 to the fourth kilometers. If you wanted to know the first three digits were significant, you would write 6.50 times 10 to the fourth kilometers. In order to write a number in scientific notation, use the following two steps. Step 1. Determine m by moving the decimal point in the original number to the left or right so that only one non-zero digit remains to the left of the decimal point, and delete all zeros that are not significant. Step 2. Determine n by counting the number of places you have moved the decimal point. If you moved it to the left, n is positive. If you moved it to the right, n is negative. Mathematical operations using scientific notation. Addition and subtraction. If the exponents of the two numbers you are adding or subtracting differ, rewrite one of the numbers so that both numbers have the same exponent. Then, to find the new value of m, find the sum or difference of the m values of the two numbers, and keep the same value of n. Mathematical operations using scientific notation, multiplication and division. Step 1. To find the value of m in a product, multiply the two values of m. Step 2. To find the value of n in a product, add the two values of n. For division, the first step in order to find the value of m, meaning in a quotient, divide the first value of m by the second value of m. Then, in order to find the value for n in a quotient, subtract the value of the second n from the first value of n. Often,
scientists sometimes need to express measurements using numbers that are very large or very small. For example, the speed of light through space is about 300 million meters per second. 8 zeros is a lot of zeros to keep track of when performing a calculation. You can express values as a number multiplied by a power of 10. This is called scientific notation. There are 8 decimal places to the right of the 3 in 300 million. So using scientific notation, the speed of light through space is written as 3 times 10 to the 8th meters per second.
Seventh main idea. Sample problems are guides to solving similar types of problems. Learning to analyze and solve such problems requires practice and a logical approach. In this portion of the lecture, you'll review a process that can help you analyze problems effectively. Step 1, analyze. The first step is to read the problem carefully at least twice and to analyze the information in it. Identify and list the data in the problem and identify what you are being asked to find. Step 2, plan. The second step is to develop a plan for solving the problem. The plan should show how the information given is to be used to find the unknown. It is often helpful to draw a picture that represents the problem to help you visualize the problem. Then decide which conversion factors, mathematical formulas, or chemical principles you will need to solve the problem. Your plan might suggest a single calculation or a series of them involving different conversion factors. Once you have a plan on how you need to proceed, you may wish to sketch out the stages of your solution in a tablet or on a flowchart. Step 3, solve. The third step is using the data and conversion factors to carry out your plan. Make sure to keep track of the units and to round the results to the correct number of significant figures. Step 4. Check your work. Examine your answer to determine if it is reasonable. Make sure that the units in the answer are what you would expect. Use simpler, rounded numbers and repeat the calculations to check the order of magnitude for your answer. 8th main idea. Variables that are directly proportional increase or decrease by the same factor. Two quantities are directly proportional to each other if dividing one by the other gives a constant value. When two variables, for example x and y, are directly proportional to each other, the relationship can be expressed as y alpha x, which is read as y is proportional to x. The equation on the bottom right of your screen should look familiar because it shows that a directly proportional relationship is a straight line with a slope of k. For example, the quantities, mass and volume, are proportional. The table on the screen here shows the measured mass and volume of 5 separate samples of aluminum. As the masses of the samples increase, their volumes increase by the same factor. The equation that was on the bottom left of your screen on the previous slide shows that there is a constant ratio between the values of the two quantities as long as they are directly proportional. Note that the data in the table have ratios that are nearly equal, indicating a relationship that is directly proportional. The graph on your screen here, including of every directly proportional relationship, will also pass through the origin, or the data point 0, 0. Both the values in the third column of the table and the graph demonstrate that the data in the table are directly proportional. 9th main idea. Quantities are inversely proportional if one decreases in value when the other increases. Two quantities are inversely proportional to each other if multiplying them gives a constant value. For example, the amount of time it takes to travel a certain distance is inversely proportional to the speed of travel. The greater the speed, the less time is needed to go a certain distance. When two variables, x and y, are inversely proportional to each other, the relationship can be expressed as y alpha 1 over x. Again, this is read as y is proportional to 1 divided by x. The relationship can be expressed in the form using a proportionality constant, which is k is equal to x times y. This equation shows that the product of the two variables will yield a constant value. The table on your screen here shows that the pressure and volume of a sample of nitrogen gas are inversely proportional. Here it is the product, meaning multiplication, of the pressure and volume at any particular time as almost exactly the same. The graph of an inversely proportional relationship is a hyperbola. An example of such a graph is given on the screen here to the right, showing the data from the table on the left. The end of the graph approaches the x-axis and y-axis, because as one value moves away from 0, the other value must approach 0.
Two variables are directly proportional when their quotient is constant. In this example, when we divide the mass by the volume, we get a constant. From the graph, we see that when variables are directly proportional, when one increases, so does the other. Two quantities are inversely proportional when they have a constant product. In this example, when we multiply the volume and the pressure, we get a constant. From the graph, we see that when variables are inversely proportional, when one increases, the other decreases.
At this point, you should be able to distinguish between accuracy and precision, determine the number of significant figures in measurements, perform mathematical operations involving significant figures, convert measurements into scientific notation, and distinguish between inversely and directly proportional relationships.